Hello everybody. Some students have asked me about their mini project, how you can convert OD per minute into, let's say, concentration per minute. And both are obviously valid rates for an enzyme reaction, but sometimes it is preferred to have concentration per minute instead of OD per minute. So how do you do that? Well, you know that OD, optical density or absorbance, which is a better term, is, according to the Beer-Lambert law, is concentration times the extinction coefficient times the path length. And I think most people use 1 centimeter cuvette, so that is very easy here. And in order to convert OD per minute into concentration per minute, all you need to do really is divide both sides of the equation by minute, and you got this. So if you want to have it all in concentration per minute, you bring these two to the other side, and you basically have OD per minute times 1 over the extinction coefficient times the path length equals concentration per minute. So that's a fairly easy conversion. So let's say you have an OD per minute. OD per minute equals, let's say, 0.1. So you measure 0.1 change per minute. Your extinction coefficient is, let's say, 1,000 per mole and per centimeter, and your path length is 1 centimeter. You can easily convert this 0.1 OD, so 0.1 OD per minute is equal to 0.1 OD per minute. 0.1 per minute times 1 over 1,000 per molar and per centimeter. That's the extinction coefficient times 1 centimeter. You see the centimeters cancel out, and you just have this one here. So you would have your concentration per minute equals 0.1 divided by 1,000, and we have minutes and molar. So that would give you 1 times 10 to the minus 4 molar per minute. So that would be your concentration per minute. Some people also want to do that as not as a concentration per minute. Some people want to do that as an amount per minute. And then in this case, what you need to do is you need to convert the concentration into an amount, and you can do that very easily with, for example, dimensional analysis. You can say my amount per minute, that is what we are looking for, equals, now the concentration is given in mole per liter, so concentration mole per liter, and of course we've got the minutes here. So we want it in mole per liter. So we want the mole, and therefore we have to multiply that with the volume of your cuvette, volume of cuvette. So what you get is, if you want it as amount per minute, then you have the concentration times the volume of the cuvette. And this is not the path length, this is the total volume. I think this is 3 milliliters divided by minute. So you can choose either way. You can choose it as concentration per minute. You can express it as amount per minute. Or you can also express the rate as OD per minute. Either way is good. So let's quickly check if we did this experiment here in a 3 milliliter cuvette here. So we've got our speed was 1 times 10 to the minus 4, 1 times 10 to the minus 4 molar per minute, and we have 3 milliliters, so that is volume equals 3 times 10 to the minus 3 liter. So our amount in this case would be 1 times 10 to the minus 4 mole per liter minute times 3 times 10 to the minus 3 liter. And this, of course, gives you 3 times 10 to the minus 7 mole. The liter cancel out, and you have down here minute. So as I said, in your graphs, so if you do, let's say, a Michaelis-Menten graph with substrate concentration here, and here the rate, you can express it as OD per minute. You can express it as concentration per minute, or you can express it as amount per minute. The shape of the graph will always be the same. So there is no change. So if your graph looks funny, then this is not because you made a mistake in the conversion. It is just simply because your data might not be terribly good. So if your graph looks, let's say, like this, then this is not due to a mistake in the conversion. It is just simply your data are a little bit, well, there's room for improvement. So I hope this makes sense, and thank you for watching.